Hi guys, today we're going to continue our lesson on stereoisomers. I just want to do a quick little review with a little flowchart. And you can see on the screen that I have stereoisomers, kind of that umbrella that we've been talking about, broken down into enantiomers. And enantiomers, as you know, just mean non-superimposable mirror images. A good example of that are your hands. They're mirror images, but they are not superimposable one on top of the other. So that's one type of stereoisomer. The other type of stereoisomer is diastereomer. And diastereomers are not mirror images of each other. So they're not mirror images, and that's kind of where we're focusing today. So there's things that I've already mentioned to you this year that are considered diastereomers, and that would be our cis-trans isomers. Cis-trans results from restricted bond rotation, whether we're looking at something that might have a multiple bond like a double bond or something that is a ring structure. So it has restricted movement or restricted rotation, and so it forms two different compounds, the same bonding pattern, but the compounds are different because you have one in the cis conformation and the other in the trans conformation, and they are not mirror images of each other. So they're considered diastereomers. The other one is what we're going to be talking about today, and it's really anything other than a cis-trans that has chiral centers, specifically two or more chiral centers. So what we're going to talk about today are the types that fall under that category. So we're going to be looking at diastereomers that have two or more chiral centers but are not enantiomers of each other. And so we're going to look at some terms that go along with that and some structures that fall under that category. So it's pretty common to find molecules that have two or more chiral centers or chiral carbons, and we can determine the number of possible configurations that they would have by a simple formula, and that simple formula is 2 to the n. And you can see that right here. So if we had n equals 2, and n being the number of chiral carbons, then 2 to the second power would mean that we have 4 possible configurations. If I had n equals 3, I would have 2 to the third, or 8 possible configurations. So you can see how tedious this can become the more chiral carbons or chiral centers that you have. And notice that I said the word possible. We can have less than the maximum calculated, and if that happens, we say that the compound is a meso compound, and we're going to look at that as well today. So when a structure is not an enantiomer of another structure, the structures, when compared to each other, are called diastereomers, and they have different physical and chemical properties and a different arrangement of atoms in the structure. So we're going to take a look at this example, and it says here, draw all the possible stereoisomers of 2,3,4-trichlorobutanol. So we know butanol is an aldehyde. The aldehyde has to be on carbon 1. So that when I draw these into Fischer projections, so I'm going to take this line structure and draw it into a Fischer projection, I'm going to be starting with this side of the molecule at carbon 1. So I'm going to have the CHO at the top, and I'm going to have a line all the way down, and then I have the CH2 Cl at the bottom with my 2 chiral carbons in the center. This is one of the chiral carbons, this is the other chiral carbon, and then this portion here is that CHCl2. So what I'm going to do is write the Cl's first, and then the other thing that's bonded there on that line structure would be hydrogens. So that's my first structure, and I'm going to call this structure A. Now the next possible structure, I'm just going to draw the mirror image of this. So I'm just going to flip this Fischer projection, keeping the CHO at the top, and then the CH2CL at the bottom. I'm going to call this structure B. And all I'm going to do are flip those CLs to the other side, like so, and flip the hydrogens to the other side. And if you look at those molecules, or those Fisher projections, you can see that they're non-superimposable mirror images. So A and B would be enantiomers. Now, there is another possibility of drawing these structures. So let me show you, and maybe you can already see what that possibility is. I'm just going to draw in my chiral carbons. Now, what if I had a Cl on this side and a Cl on the left-hand side, like so? If you compare that to A and B, it is nothing like A and B. Yes, it has chloros on 2 and 3, but the placement of those chloros is different. I have one on the right side on carbon 2 and one on the left side on carbon 3. So the placement of those chloros in that Fisher projection is different than the placement that you see in structures A and structure B, where I put the CLs either on the right-hand side or the left-hand side. Okay. Now I can draw a mirror image of structure C. I'm going to call this one structure C. And I'm going to draw the last structure, because we can have 4 possible structures because I have 2 chiral carbons. And I'm going to flip these CLs like so, put my hydrogens in, and I'm going to call this one structure D, so we can stay organized when we discuss. So structure D is a mirror image to structure C, and it is non-superimposable. No matter how I pick that up and place it on top of the other one, maybe I turn it 180 degrees, it doesn't matter. I will not get every molecule to line up with the same molecule or same atom. Okay, so C and D would still be enantiomers. Now, I forgot to talk about chiral carbons and looking at that formula, but I have 2 chiral carbons, so I would have 2 to the second power, or 4 possible structures. And I drew the 4 possible structures there. Now, we can say that A and B are enantiomers, so I'm going to write this out. So A and B and C and D are enantiomers, right? They're non-superimposable mirror images. Now, is there any relationship between A and C or A and D? There really is no relationship there, except that they have chloros on carbon 2 and carbon 3, but the placement of those chloros is different. So we have a different arrangement of atoms. We would also have different physical and chemical properties here. So what we would say here is A and C, D are diastereomers. We could also say that B and C and D are diastereomers. I'm not going to be able to fit that on there, but you know what I mean. So A and B and C and D are enantiomers, but A does not have a relationship with C, nor does it have a relationship with D. They're not mirror images. They might, and they're not superimposable either, but they're not mirror images. So because they're not enantiomers, we call them diastereomers. So A would be a diastereomer of C and D, and B would also be a diastereomer of C and D. As I mentioned earlier in this lesson, I said that meso compounds have fewer than the possible or predicted configurations, and that's due to the chiral centers being bonded to the same non-identical groups. And what I like to say is that there's a plane of symmetry in these molecules, and I'll show you what I mean. Tartaric acid is a pretty good example of a meso compound, so we're going to take a look at that example next. So here is the structure for tartaric acid. Tartaric acid has 2 carboxylic acids, so you can see one carboxylic acid on this end and another carboxylic acid on this end, and then you have OH groups coming off of those interior carbons. So if I look at the carboxylic acids, I know that those carbons are not chiral carbons because there's a C double bonded to an O. So the carboxylic acids would not be chiral carbons, but the carbons that the OHs are on, if you look at what's bonded to them, they each have 4 different attachments. So those carbons would be chiral carbons. So I have a chiral carbon here and a chiral carbon here. It'll be easier to see when I put these into Fisher projections, which I'm going to do right now. So I'm going to put a COOH at the top, and I have 2 chiral carbons, and then I have another COOH or carboxylic acid at the bottom, and then I have OHs and H's on those interior carbons that are chiral. So this is what the Fisher projection would look like. And I'm going to call this A. Okay? And I'm going to draw the mirror image right away, so I'm just going to flip those OHs to the left-hand side and rewrite the structure. So I have the COOH staying at the top, going to the COOH at the bottom, and I'm going to flip these OHs to the other side and put my mirror image in like so. Okay, so I have my structures A and B. So this is B. So if you look closely at structures A and B, they are actually identical structures. And the reason that they're identical is because if I draw a plane of symmetry down the middle in between those 2 chiral carbons, and I folded this in half, the carboxylic acid COOH on the bottom would line up with the COOH on the top, this H with this H, this OH with this OH, and like I said, those 2 things would line up as well. I have a plane of symmetry, so they are identical. Also, if I picked B up out of the page and I turned it 180 degrees, the OHs would line up, the H's would line up, and so would the carboxylic acids. So we can say that A and B are actually identical. And we call, because remember we have 2 chiral carbons, so 2 to the 2nd power is 4 possible structures. But even if I drew the other structure, the C and D, I would still have, and I'll do that for you over here. If I put an OH here, and an OH here, and an H here, and an H here, I would still have a plane of symmetry. So I could say that if this were C and I drew D, C and D are also identical. Okay? So what this is telling me is that I have fewer than the 4 possible isomers. So, or 4 possible structures. So we call this a meso compound. Because it does not have 4 different structures. It has 2 structures, and they are diastereomers. They are not identical. A and B are identical, so that's 1 structure. And then if I drew out, and I'll just draw it so you guys can see this structure as well. And I flip this like so, I would have a plane of symmetry. And if I took this and I turned it 180 degrees and plopped it down on letter C structure, they would be identical. So they are, yes, they look like mirror images, but they are actually identical structures. So we really only have 2 different structures, A and C, or B and D, whichever ones you choose, but they are what are the different structures, and they would be what we consider a meso compound tartaric acid, because it does not have the 4 total structures. It only has 2, because we have those identical plane of symmetry structures. I hope you found that helpful, seeing what the diastereomers are and meso compounds. There are some examples in your textbook, the same examples that I did in the slideshow. If you need some extra help, I would also like to mention that I have a Professor Dave Explains video that talks more about diastereomers and meso compounds. If you want to take a look at that video as well, it is on the class page. If you have any questions, you can email me or wait and ask in class on Wednesday. But your homework for tonight is page 578, 39, 40, 48, and 50. That's due in class. Tomorrow we'll go over it tomorrow in class, and I will take any questions if there are any questions on diastereomers and meso compounds. All right, guys, have a great rest of your day, and I'll see you tomorrow.